All right, good afternoon. Any other questions?
You got any plans for Valentine's Day?
No. Yeah, but happy Valentine's to everyone, and good luck with all your plans.
Oh, you said colon backslash. So is that?
I don't believe it because you can't have a backslash. But it's true that I had it in the slides because I remember seeing the two symmetric things. I have to take it out of the slides. All right, so today we're going to start talking about what it means to translate a programming language from the source code into whatever its final destination may be. So just imagine that you're writing your code in your favorite programming language, and so what happens with it? So you write a bunch of source code in Java, for example, or in Scala, and there's three main phases of processing that we distinguish. The first one is the simplest. It's called lexical analysis. So you have a bunch of characters, long stream of characters, and we want to group them into what's called tokens. A token could be a reserved word, such as if or while. It could be an identifier, such as N123 or whatever. A literal, like 0x123 or 0.5 or whatever. Operators, comments, whatever other features the language has where it thinks in terms of tokens and not characters. So that's the step we're going to be looking at today, and it's called lexical analysis. In the second step, we will have a stream of tokens, and we want to turn them into a data structure that is useful for us for generating code. So we will want to build a representation. That representation is usually called a parse tree because it is in some way a tree-shaped data structure, but it doesn't mean that we will actually make a tree. We will make a data structure of something that has children and descendants and so on. Then that data structure is used normally to generate code. So the code generator will walk through that data structure and produce instructions for either a real machine or for a virtual machine, such as an Intel processor or an ARM processor, or on the other hand, something like the Java or Python virtual machine. There are also things called interpreters, although they're getting kind of rare these days. An interpreter will not actually generate any code, but instead will directly execute the code that you write by inspecting the data structure that the parser built up and kind of walking through it and, so to speak, simulating or hand, not hand executing, but mechanically executing the pieces of the program that you wrote. So years and years ago, these interpreters were very common. You may meet someone my age who fondly remembers that they grew up with something called BASIC, and they might tell you that they got some little machine for Christmas where they could program things in BASIC, and that was an interpreted thing. Each line of the program was kind of simulated as at a time without ever generating machine code. So let's look at the lexical analysis phase in a little bit more detail. There are a few things one worries about. So we want to remove unimportant white space from the program. White space normally is not significant, although in the next slide you'll see that there's some exceptions. We'll remove comments. Comments are never used when the program is translated. We break the input into tokens. So here, for example, I have a sample input in some mythical programming language. This might be a valid a piece of code. Then we do not want to have an I and then an F. We want to have the if all together, and we want it to be tagged as a keyword. Then over here, we want this one to be tagged as something that's an identifier, but not a keyword. We want the greater and the equal to be grouped together as a single operator, and distinct from a greater followed by an equal. Right? That's because it's a meaningful thing for us. We want the 0.0 to be together. as a single floating point number. And the rest is more of the same. So we'll be using regular expressions to do that grouping. There are other ways of doing it, but regular expressions is simple for us to do, and it's something useful to know anyway. Now, in some programming languages, there's other things that need to be done. For example, in C and C++, you have to process these pesky header files. So in C and C++, it might say pound include and then some file, and then the compiler has to actually find that other file, open it up, and also tokenize it. Yeah?
What do the people who program languages like Rust or whatever have to program the thing that does this lexical analysis in?
Probably Rust.
So they program the thing that analyzes Rust in Rust.
That's common when, like the Scala compiler is written in Scala. Of course, it was not always written in the Scala that we have today. So typically when a new language is developed, you write the compiler, the first version of the compiler in some other language. But then eventually your language is, of course, so much better, otherwise you wouldn't be creating it, that you will move. Now you already have a compiler, right, written in another language, and so then you start moving it to your own language.
How does that work?
You just compile it with the older version.
Oh, okay.
And then now you have an executable for the newer version. So there's a bit of a bootstrapping process going on. But it doesn't have to be like that. I mean, you could perfectly well write a compiler in any language, in Java or in C or something. But commonly people enjoy using their own language. Yeah.
So just to clarify, even if you have a compiler written in your own language, at some point it had to be verified by a compiler written.
Well, the proto-compiler had to be in another language, right? Because your language didn't exist yet. Yeah. That's always true, and there's no reason why it has to be in your language. There's some languages where the compiler is written in C with Lex and Yak, and it just forever stays like that because it's not worth having it self-hosting. I just happen to know that the Scala compiler is written in Scala, and it's a very complex piece of Scala code actually. And the Java compiler is also written in Java, but of course. That happens over time. Like I have no idea what Python, whether there's any Python in the Python compiler or whether it's all in C. So back to the header files, they're a bit of a pesky issue because they're also think of how you can do a pound define in C, where you can say pound define, then some word, and you can replace it with anything at all, and so that has to happen before parsing, because it has you can make definitions that are not meaningful in the parsing stage. You can inject arbitrary tokens. Not necessarily a great concept, which is why I've never seen it in any other language than C and C++. So that's definitely a concept that has not withstood the test of time. So a couple of notes on whitespace. In most languages that whitespace is it's either completely optional, or sometimes you have to have one space, like between keywords or between tokens, but you could also have an arbitrary amount of space. So that's what's called a free-form language. There are languages where every statement has to be in a separate line. Fortran is like that. You don't know Fortran probably, and it doesn't really matter. But in the olden days, Fortran was actually put on punched cards, and so every card was its own statement. So no, I've never seen anything like that today anymore. So in Scala, it's a little bit in the middle because sometimes a new line is significant. So a new line there's a phase in the Scala compiler when it ponders whether a new line should be translated into a semicolon. So the Scala grammar has semicolons, but it also has this concept of new lines. And so it's a little bit difficult for it to do that, but that's a part of the lexical analysis. That happens before the Scala compiler has much of any idea of the structure of the program. In Python, famously, we have indentation by block structure. So you put some number of spaces, and that indicates that these two statements, for example, are nested inside this statement. That is kind of a good idea, actually, and it's surprising that it's not popular with other languages. The designer of Python had a simple reason why he chose to do that. He didn't want people to argue about where to put the braces of the begin-end statement. By not having any, that argument was completely lost. And then he snatched defeat from the jaws of victory by allowing people to use a mixture of tabs and spaces for indentation. And now people argue about whether to use tabs or spaces. So that's unfortunate. So if you were to ever follow this scheme in the language that you design, stick with one or the other. Yeah, with these kind of things, choice is bad. So after we have our input tokenized, the next phase is to build up a parse tree. So here I'm giving an example of such a tree. So my input expression is 3 plus 4 times x. And the parse tree should not just mechanically look at this, but it needs to know about the semantics of these operators. So I guess that's the difference between the lexical analysis that really is just a mechanical chopping up and parsing, which needs to build a much more sophisticated data structure that takes the semantics into account. So here we want the multiplication to happen first, and this parse tree accurately reflects that. You can see there's a plus, and the 3 is combined with the product of 4 and x. So something that we will start doing the week after next is to systematically translate these kinds of things into these data structures. Now here I drew it as a tree like you might see in 46B, where you have nodes and children and leaves and that kind of thing. That's not actually what we do. We will build up a data structure for this, a Scala data structure, very similar to that in Homework 1. Remember in Homework 1 we had like operators and variables. No, we didn't have variables yet, but we had constants and it'll be those kinds of classes. We will be doing a couple of very simple languages, and we will be following essentially the same approach. You'll see that starting next week, and the homework number 5 will make you do some of that. So this is, of course, a very simple structure still, because expressions aren't all that complicated. Higher level features have much more substructure. So think about what a function needs to be when it's parsed. We need, of course, to have the name of the function. We need to have the names and types of all of the parameters. So there needs to be a data structure, something like a class function, that has a instance variable for the name, that has a list of parameters. Each parameter has a name and a type. A type is something that's complex in itself, because a type could be a simple type or a compound type, like a list of something. And then we need to translate the entire body of the function as some sequence of statements or expressions, depending on your programming language. And so you're going to have a big old data structure that represents everything that's there about this function. So building up these data structures is the process called parsing. And in a compiler construction course, you would learn many ways of doing that parsing quickly and efficiently. In this course, we will be just using a parser that's simple to understand. There's one that comes with Scala that works easily for the kinds of languages that we need to do, and we'll just leave it at that, because we're not really interested in the intricacies of the process. We just want to have a basic overview of it. Now, when you have a parse tree, then time comes to generate code. And so the whole point of having that the parsed data structure is to make code generation possible and hopefully easy. So if I have this particular tree here for this expression, it needs to be translated into some sequence of assembly instructions. So over here, here are my resulting assembly instructions. And so someone has to go through this thing and then say, okay, how do I do this? Well, I guess I have to and maybe this is not the most logical set of instructions, because really if you think of what you want to do is you want to get the 3 into memory, and then you want to compute this expression, and then you want to add them, whereas the instructions that I have here do it in the opposite order. These 2 instructions here compute the product, and then they just add the 3 to this. So that's it's always a good question on how one does that code generation. We will actually do that with a very, very simple language, because it's a tedious process, and we will be generating Java virtual machine instructions. instead of these Intel instructions. And we will be relying on the library to do most of the dirty work, because it is also tedious to do that. But it's interesting to see that process in action once. Now, a compiler will also do other things that we will not actually be implementing ourselves. So there's various optimizations that compilers are really good at carrying out. The first one is, and that's kind of similar to what you've seen before. So if I have an expression that I need to have computed, then the naive way of generating code will take two things into the processor, combine them by adding or multiplying them, and save the result back out to the stack. And then it'll repeat doing that for all the other sub-expressions. Clearly, that's not the most efficient way of doing it. The better way of doing that would be, if there are not too many different variable parts, is to get them all into a register and then do all the computations with registers. And that's something that an optimizer knows how to do. I don't particularly know how to do this, but in a compiler construction course, you might learn how to do that. Another thing that a compiler will do is optimizing things in loops. Here's a very naive example. Here I have a loop that, with the statement here, doesn't actually have to be in the loop, because the inputs to the statement don't change in the loop. Now you might say, why didn't the programmer move it out of the loop? But if you look at your loops, you'll see that you will have done similar things. So we often write things inside a loop just because it's handy to have it there. It makes it easier to read, not necessarily because it needs to be recomputed every time. So an optimizer will say, hey, this thing doesn't need to be computed, and it'll compute it once outside the loop, and then you keep using it in the loop. Another kind of optimization that might happen in loops is, if you think of a typical loop that walks through an array, where I goes from 0, I is less than the length of the array, I plus plus, and then you have an A bracket I. Well, in Java, every A bracket I is checked, is range checked. Every time that you access an array, there's a cost to it, right? You need to see, is the index in fact valid? Now that seems like a complete waste. If you know that I starts at 0, it gets incremented every time until it reaches the length of the array. You know for sure that those checks are not necessary. Now the Java compiler cannot do anything about that, because the Java compiler generates virtual machine instructions. There is no virtual machine instruction for access the ith slot without a range check. There's only one virtual machine instruction that says access the ith slot. But the virtual machine itself has a second optimization phase. When the virtual machine looks at the Java virtual machine instructions, it does not simulate them. It used to 25 years ago. It just simulated them, but nowadays it translates them into actual machine code through this thing called the hotspot compiler. And so it will optimize out unnecessary checks. And that's, of course, a really important thing. If you think about, all we're talking about this course is high-level languages. When these kind of programming languages first came out, they had to compete with what people programmed in up to that point in assembly. So nowadays, almost no one programs in assembly anymore. But it used to be, my first paid job was to be an assembly programmer, and it was no fun, right? I mean, it was tedious and slow and error prone. And so as soon as C came along and C promised that the code that it could generate was going to be almost as fast as assembly code, everyone jumped at it. And so the reason C could do that is because it was very close to what assembly is. So if you know assembly, you can you can visualize exactly what the C compiler does. Then they tossed in a few good optimizations, and it was not a hard stretch to see that anything that you could do in assembly, you could express in C. Once in a while, I remember when I first started with that, I'd have to open up like a little hole in the program and hand code a little bit of assembly in between. But that was really few and far between, and only if you measured that was actually a beneficial thing. And so then when other languages like Java came out, people said, oh, this is going to be terrible. Java is never going to be performant because it had a virtual machine and all of that. Nowadays, the virtual machines are very fast, and in many ways, there's some instances when they can do optimizations that a compiler simply couldn't do. And I'll come to that in a minute. So it is essential for programming, for higher level programming languages to be successful, that they have these optimizations. So here's another example of one that's very common and good to know about. So when you have a short function, like here I have max, and so max is just a few lines of code, and assembly is also a few lines of code, one comparison, and that's it. Of course, as a programmer, you want to be able to write max, because if you always had to look at this mess of question mark colons, then it would make your program harder to read. In C, it was common to make a macro for max, a pound-defined thing, so that one didn't actually call the function. But nowadays, we don't really do that anymore, because the compilers are perfectly good. They know when a function is short and when it should be just inline replaced. And so they know all of the rules and when the inline replacement makes sense. And that's a really important part, because it means that we as programmers, we can use functions, and we can leave it to the compiler to decide when is it beneficial to do the inlining. This is the place, by the way, where a virtual machine sometimes knows more than a compiler. Think of all the Java functions that you've ever written. I bet you that half of your Java functions did nothing but return X or return name or something. Right? You have all of these getters and setters, and you do them because your instructor tells you you're a bad person if you don't write them. And so, have you ever thought of the cost? I mean, each of those things, it needs to call the function, okay? And there is an actual cost to calling a function. There's, of course, the cost of the extra instruction, but there's a more important cost. What's really expensive about calling a function? Yeah.
Going to the memory to get that line of code.
So going to memory is bad, but there's another thing about calling a function that's even worse. Yes?
You have to push and pop from the stack frame.
That's bad, but there's something that's much, much worse.
It might modify state.
What the heck is the term?
So I hope they teach you these things in 147. So when I was young, what they taught me in my equivalent of 147 is, here's what a processor does when in each cycle. First it fetches the instruction, then it decodes the instruction, then it executes the instruction, then it fetches the next instruction. That was actually true in 1975. Nowadays, it is not true. So the processor fetches the instruction, and it decodes, and at the same time it fetches the next instruction. Mm-hmm. And then it starts executing. It's already fetched the next instruction, and decodes and fetches and decodes. And then it has multiple instructions, and it tries to run them in parallel when it can. Because if one of the instructions says move something into AX and the other one says move something to BX, it can perfectly well parallelize them. If one of the instructions says add AX and BX and the other says something with CX, it'll parallelize those things. So a modern processor absolutely critically depends on the ability to take a whole stream of instructions, reorder them if necessary, parallelize them, and so that it can do many of these things at the same time. If you deprive a processor from that, then you see a big hit. And so anytime that you have a jump somewhere else, then it has to throw away its entire prefetch queue and start over. And like you point out, then it has to go to a different location in memory, which may not be in cache currently. And so that's always all a big mess. Now you might say, is this a real problem? And it's easy enough to see from profiling that it makes a huge difference whether you can do inlining or not. And the other place where you can see just how important it is you've heard of these recent hacks, maybe? Exactly. Those hacks actually used the fact that the processor does this code analysis, and it leaves subtle traces about what it does. So, it fetches some variable, and then it leaves it somewhere where some attacker could actually observe it. So to turn that off in a hurry, some of the fixes actually have to slow down this prefetching, and it's a real hit in processor time. They say 15% or something. And that's huge. I mean, for the processor to regain that just by raw power is going to take 10 years. So the speed gains are so slow nowadays that the only speed gain you get is by scaling up. And so it's an important thing. Now, hopefully they're going to figure out how to fix these things. But
I think the hit is more than 15%.
It seems to depend very much on the on the load, right? Yeah.
Some
but
programs are hit 50%.
Yeah, but it could be substantial, and so it just really illustrates as to how important this this parallelization process is. All right, so now let's go back to lexical analysis. So the tool of choice for building a lexical analyzer for us is to deal with regular expressions. Is there anyone here who has never heard anything about regular expressions? There were a whole bunch in the other section. Okay, so we have a few. So I will give you regular expression 101 real quick, and then ask questions on Piazza if you need to solve specific problems. So conceptually, regular expressions are super simple. There's only three things you need to know. Or four things, I guess. So generally in a regular expression, a symbol stands for itself. If I write, like here I have a regular expression where I say E. The E means it needs to match an E. Here it says 0 or 1. It needs to match 0, 1, and so on. There are a few symbols that have special meaning. In this particular regular expression dialect, parentheses have a special meaning, the vertical bar and the asterisk. We will later introduce a few other characters with special meanings. So concatenation of regular expression means if alpha and beta are a regular expression, then alpha beta means we first need to match alpha, and then we need to match beta. In the example over here, E is a regular expression. It's a letter that stands for itself. This whole thing with the parentheses, as we will see later soon, is a regular expression. And so we first need to match E, and then we need to match the thing that comes afterwards. That's what's called concatenation. Concept number 2 is alternation. If I write a regular expression and a vertical bar in another one, that means I should match one or the other. And here is an example. I need to match either 0 or 1 or 2 or 3 or so on. And the third one is repetition. So the asterisk means I need to match 0 or more sequences. So over here, I'm repeating this part here. The parentheses are necessary to indicate which part I repeat. And that means I can have no digits, or 1, or 2, or whatever. And they don't have to be the same digit. So for example, E1, 2, 3 is a match for this particular regular expression, because the E matches the E, and then the 1, 2, 3 matches this one here, since it's a sequence of the things inside. So with these three operations, concatenation, alternation, and repetition, those are the three primitive operations for forming regular expressions. And that's really all you need. In real life, when you have a regular expression syntax, there's a whole bunch of different convenience notations to make common forms a little bit nicer. So I will introduce some of them. For example, it often happens that you want one or more of something. And of course, you could always say, whatever your regular expression is, give me that, and then give me 0 or more of that. But if the regular expression itself has a bit of substructure, then that's boring to have to repeat it. And so alpha plus is a shortcut for that says 1 or more. Alpha question mark means 0 or 1. Then you've seen here that it was tedious and boring to have to say 0 vertical bar, 1 vertical bar, and all of that stuff. So anytime that you have characters that kind of behave similar, you put them into what's called a character class. The bracket notation means I want x, y, or z. If you say x dash y, then that means everything in a range of characters. So here, for example, when I say 0-9, that's all of the ASCII digits. When you have a character class, you can form its complement. The complement of x to y means everything other than x in this range. And you can, with any character class, you can pack other things in there. You can use this complement notation. You cannot use the complement outside a character class. So you could not say, like in this example here, I couldn't like stick a complement for the entire thing. The only thing that's complementable is a character class. Then every regular expression language, and unfortunately there's more than one of them, has its own special syntax for all sorts of other stuff. So in Java there's like 20 other things that you can express, and Perl has a different and incompatible dialect, and JavaScript has minor differences. Yes?
Perl's is unique. I thought Perl was like the de facto for regular expression.
No, I mean, Java and Perl have annoying differences.
Oh, man.
And the Perl and grep have annoying differences, and the extended grep and Perl have annoying differences. So there is any number of different regular expression languages, and so the first thing when you find yourself having to use them in earnest is you just have to Google what the special rules are for each of them. It's a pain. It would be really nice if those had somehow been more unified, but they're not. Now, one thing that we will often need to do is we will need to express that we won't have any letter. Like if you have an identifier, right? It's a sequence of letters. And in the olden days, you would have said a letter is something between A and Z. Okay, uppercase A and Z and lowercase A and Z. But in 2018, most programming languages will allow you to use letters in any language, not just English. So like a Chinese programmer might perfectly well want to use Chinese letters for variable names. Certainly a German user might want to use umlauts. And so most modern programming languages say that when this language spec says letter, that means any Unicode character that has an attribute letter. There's about 100,000 Unicode characters, and some fraction of them are letters. Yeah.
In modern day languages, can you use tokens in different languages? Like, can you say if in like Chinese?
No, I've never seen that. I mean, that's actually not true. There's one place where I've seen it, in Excel. Yes, in Excel. Yes, if you do Excel in French, all the functions are translated, and it is super irritating.
It's pretty funny.
But no, most programmers do seem to resign themselves to just learning those tokens in English. But there's no reason why it has to be like that, right? I've seen a couple of languages that were for like secondary school children, where they did make an effort to translate the keywords into the local language. But I've certainly seen it many times that people would just write the program in their own language, and everything was in their language except for the keywords of the language itself. And so that's perfectly acceptable. In Java, you can write your source code, with in any language. And so because of that, I would generally not use 0 to 9, but I will use the Unicode equivalent, which is \P followed by either L for letters, N for numbers, or Z for space. Yeah.
Just a quick clarification on that notation previous to that one. Is it all characters X through Y? So if I change that to like C or something, would it be all characters other than the ones C?
Yeah, this one here with the hat means it's everything other than what you list further on. So this is not a complete example. If you were to, for example, say caret 0 to 9 A, B, C, then that means it's everything that's not a 0 to 9 or A or B or C. Or if you say a hat and then \PL, that means everything that's not a letter. For that, actually, we have a shortcut. You can say \uppercase P. So that's the complement of that character class. Then finally, dot matches any character. And if you need to escape one of these characters with special meanings, then you use a \. So if I say \. Dot, that means an actual period. \/ means the \. It's a little unhappy in Java when you have a regular expression that contains a \, that because it's inside a Java string, of course you have to escape that \, too. So you end up writing \, when you mean a \. We'll see that Scala offers us some relief from that. So you have a few examples. So this regular expression here, it has maybe a plus or minus, followed by a sequence of digits. Or a better way of saying that would probably be maybe a plus or minus, followed by numbers in whatever language you may have. There's some languages that do not use the digits that we're familiar with. So this would be an integer. Here's one for hexadecimal number. Start with 0, followed by an upper or lowercase x, then followed by a sequence of, that's what the plus indicates, at least one of them, 0 to 9, A to F, A to F. I've never seen hexadecimal numbers localized in other languages, so I think that's fair, yeah?
Can you tell them to ignore like any sort of tab or space? Or
You can write anything you want. In this case here, a tab or space would not match. If you wanted to match a tab or space, you would have to put it in.
I mean, is there like some special character where you can say just like ignore all the spaces?
No, there's no such thing.
Okay.
Although I'm sure Perl has an option for it. So let's try something. What about quoted Java strings? So here I have a quote and another quote, and inside it I can have anything at all. Well, that doesn't actually work, because this dot here will match a quote, and you might say, well, so what? If I have a quote inside the quoted string, then it's over, right? But what if it was a backslash quote? Because you can have a backslash quote inside a quoted string, right? That's what if you actually want to have a quote in there. So you now need to do that. And so so the thing that you see here is not going to trap the backslash quote either. So here I have an effort of that. I say, okay, we start with a quote, and we end with a quote. And now I have something that is either this thing or that thing. This thing says it is neither a backslash nor a quote, or neither a quote nor a backslash. And this one says it is a backslash followed by something, because it could be a backslash followed by a backslash, or a backslash followed by a quote, or maybe a backslash followed by n for a new line, right? So that looks kind of good. Maybe, then you'd have to think about, what about like backslash x or backslash u? So at this point, you're going to see that writing a correct regular expression could actually be kind of complicated. One that identifies all legal strings and rejects all illegal strings. So one's usual approach for this is, of course, that after 15 minutes, you say, well, it looks pretty difficult, so let's go to Stack Overflow. And then you're going to find 26 half-assed proposals for this particular regular expression, and then you pick the longest one. Right? That's what everyone does, and you hope that it holds up under strain. So it actually can be a little bit challenging to write these regular expressions, and so I usually find that the first one that I write is almost correct, and then the hard labor begins on actually making it bulletproof, and that part is never any fun. So there is a famous quote by programmer Jamie Zawinski, who said that, there are programmers, when they have a problem, they say, oh, I'll use a regular expression. Now they have two problems. So that's a little bit what it's like. But they are undeniably useful. So Scala has a regex library that's perfectly serviceable. We're only going to be using a couple of pieces of it, and I'll give you a telegraphic introduction into them. You need to import a thing called scala.util.matching, and then you put a ._, and that imports everything from that library. To make a regular expression, you make a string, just a regular Scala string, and you add .r that compiles it into a pattern object. So in Scala, a string has a method called .r that turns it into a regular expression. Once you have such a regular expression, there's two methods that we're going to be looking at. One is called findAllIn, and the other is called findPrefixOff. So let's look at findAllIn first. FindAllIn takes the string that you want to analyze, and then it gives us a list of match results. The easiest way to get the list of actual matches is to call toList on that thing, and then you get a list of matches. So here I have my regular expression is sequences of digits, of Latin digits, I guess Arabic digits, and then I get the matches from here, and nothing else. So that's what findAllIn does. We're not going to be using findAllIn for the lab and for the next homework, but it's obviously a useful function. What we will be using is this thing called findPrefixOff. Because our task will be that we will be having a sequence of input characters, and we want to find out, like, what's the first token in it, the first keyword or symbol or whatever. Find prefix of gets a string, and then it gives you, well, there's a possibility that the regular expression does not match the prefix, in which case it gives you a thing called an option, and I don't want to talk about options quite yet, so I'm giving you a not very nice way of dealing with them. I say, whatever this thing takes, put after it get or else null. That way you get a null if there was no match, and you get the match if there was a match. Not very Scala-ish, but we're not quite there where I can tell you what the right way of doing it is. So for right now, live with it, gives you a null, and you know how to test for null. You've done it all the time. So this particular incantation here gives me either the match, and the match has to be at the beginning. That's why it's called find prefix of. Or it gives you null if there was no match. It's simple enough. Then there is a feature called groups that we will not need today, but we will soon need it. A group is a subpart of the regular expression. If you look at this regular expression where it says some number of digits bottles, that's the string I want to match. It has to be the digits and then the string bottles. And then I can, of course, match that, and then I'll get a match here and a match here. And so that's what I'm doing here, find all in. But now I might want to know inside that string here, I want to know where is that substring with the digits, because I might actually want to process that. That's a common thing. The way you do that is you put a set of parentheses around the substring of interest. That's what's called a group. And then you can extract that group. Oops. What the heck? And the syntax for that is not very intuitive. I have to say I want to have the match data, and that's some data structure that enables me to fish out groups. I turn that into a list, and now I have a list of match data, and in each match data, I say from that match data, give me the first group. I'm just leaving it here so that if and when you need it, you can copy and paste that particular incantation. So if you've used groups before, this will be instantly familiar. If not, we'll just come back to it. So that's what you need to work with regexes, and I want to put that to work in this lab. So this lab starts out with something that I think in the interest of time I would like you not to do today, where it says write down some regular expressions. And that's all in good, clean fun. But these are actually hard to do, and you could easily fritter away a half hour coming up with a correct regular expression for something like C-style comments. And when you see here, you can see how things go into the weed quickly. So I would like you to go boldly to step 3 of the lab, because that's also what's needed for the homework assignment. So here we have the following setup. You have a list of regular expressions. Here it is, and it should work for any list of regular expressions. And you have an input string. And what I want you to program is a function that computes the first match. So it should go through the first regular expression, then the second, then the third, and so on. And it should call that find prefix of method that you have here. See if find prefix of returns, and if so, you've had a match. And the reason why is that way when you look at this input here, we'll be able to say if is a match, because as it happens, it matches the very first of these regular expressions. Then in what's called step 4 here in this lab, it says now keep doing that while there's still stuff in the string. The next thing that it'll find is the parentheses. Then it'll find the x, then it'll find the less than, then the 0, then the parenthesis, then the space, and so on. So that way, by repeatedly calling it, it'll break this thing up into a sequence of tokens, and it'll not give you a token. It'll not give you a token for R. It'll give you a token for the entire thing, for root. So that's what you want to do in lexical analysis. So try to implement these two functions. They're both very, I shouldn't say trivial recursions, but certainly very simple recursions. So boldly go into step 3 and let's get going. Here is, by the way, what I said about the shortcut that Scala offers when you have strings containing backslashes. You can make a string enclosed in triple quotation marks as opposed to single quotation marks. Then also has to end in triple quotation marks. And then there are no more any special characters. There's no backslash escape. You don't need to escape a quote. Of course, you can never put a triple quote in there, but that's life. And then that way I don't have to escape this backslash and make the regular expression more unreadable. It's your choice whether you like that or not. Okay, code away, and in 20 minutes or so we'll see what you've got. It really is, if you set up the recursion, it just writes itself, I hope. I can do this in real time here. So we have the first function, the first match, right? So we're going to be recursing on this list here. So the first case should be what if I have no patterns? So if patterns is empty, then what's my answer? No, right? Then I didn't find anything. Else? Now I need to get myself that match. There was some mumbo jumbo that I had to do with find prefix of. So let me copy that and beat it into submission. Oh, and I can't use match because match happens. Notice that match is in dark blue. That happens to be a Scala keyword. So let me just call it M. And my regex is patterns head. Find prefix of. That's my input string.
Professor,
Yeah.
we found something interesting. So we tried using, our mistake was that we tried using find first in instead of find prefix of.
Oh, I see. Yes,
we're
that.
not sure what the difference.
Find first. I'd have to look it up. I mean, I don't have these things memorized.
I think one of them returns like
Yeah.
a list of, or it returns like a regex or something.
All right. So now we have M. Now M might be null. In which case I have to keep on going. So then I have to try the others, right? So it's tokens of. Oh no, I'm the wrong thing. I should be up. I should be up here. So first match of input and the tail. What are they called? Patterns to tail. Okay, so let's try it on, see if it works. Come on, silly worksheet. Oh, because I didn't have an else here. Else I found my match, right? So how do I know? Oh, the match is M. Yeah. Okay, so now I'm getting. Come on, go away. Now I'm getting here my first match here. So if you look again at it, it is straightforward recursion, but you need to remember what are we recursing under? We're recursing the list of patterns. So we're trying the first pattern, then the next, and so on. So the key observation is if the patterns are empty, then you're done. Otherwise, you do the work. So the second one with the tokens is a little different, right? Here we're not iterating over the patterns, but we're iterating until the input is consumed.
What if you use find all and iterate over the patterns?
I don't know what find all in does. So I'm just going to follow my recipe where it says what I was supposed to do. It says recursively call this thing. Okay, so this Okay, so let's just see. So it says if the input is empty, then it's nothing else. So again, I have to now call now I have to call the first match. Val M is the first match of input tokens. Was it first match? First match. Yeah. Patterns. So if there is no match, then I guess I return nil. Yeah, then I'll just stop, and otherwise I have my match, so I cons it with tokens of that I can now just copy and paste.
Length is a method. Length is a method, right?
I'm sorry?
Length should have parentheses after.
No, it doesn't need parentheses.
Oh, really?
No.
It's not working for me with parentheses. For me, because like when I remove the parentheses, it doesn't work.
First, because I didn't call it first, it's input. That's what happens when you copy and paste. And did it work? I only got the list that goes until if.
You want to see what I did?
Just a sec. Let me try to
Okay.
think. So much for live coding here.
It should be of m.length.
Yeah, m.length, not input.length.
This left here.
So instead of input.length, do that.
Oh, yes. Yes, it should be. So this whole thing was bogus. Yeah, well, because I called it first. I see. I get it. Yes. And so then this should. Okay, I see. It's just it's input.substring.
Mm-hmm.
Yes. Of m.length. Yes. Yes. And now I have my list of tokens.
Mm-hmm. Why does mine not work without the parentheses? Oh, never mind.
Okay. So it is again a straightforward recursion.